You ever get that like deja vu feeling when antidepressants come up in conversation? There's always serotonin, brain chemistry,
Right.
but rarely a satisfying aha. So that's how it works.
They're giving us the Spark Notes version of a really complex novel.
Totally. But luckily for us, we've got a full-on investigation file today, this research paper, Pharmacos Antidepressivos, to really pick apart the how of antidepressants.
Hmm.
And you know they say, the truth is often stranger and way more interesting than fiction.
It's definitely a deep dive into the intricate, really workings of the brain and mood regulation.
So first things first,
Mm.
before we even open the medicine cabinet, got to define the problem, right? When we say depression, what are we really talking about?
It's far more than just a bad day or feeling blue or anything like that. You see, this research, it defines mood as this sort of like baseline emotional state. The almost like the background music to our lives, you know?
Okay, I like that analogy. So sometimes my background music is upbeat, other times it's a bit more mellow, maybe even a little sad. That's normal. After,
Blue. Fluctuations are just part of life. But
yeah.
with depression, that background music itself changes, and not in a way that just fades into the background, you know?
Yeah?
It becomes persistent, pervasive, and really starts to affect your quality of life.
Which is where, if I'm understanding this right, the clinical term episodes comes into play.
Yeah.
This isn't like, oh, I'm having a depressive episode because I spilled my coffee.
No, not at all. Clinically speaking, episodes have these very specific characteristics. Like we know manic episodes involve that intense energy, racing thoughts, maybe even risky behavior. And then you have depressive episodes where you see, that profound sadness, loss of interest in things you used to love, fatigue. It's a whole different experience.
So how can you tell if it's clinically significant depression, not just a case of the blues? Because it seems like everyone's saying, I'm so depressed after a rough week.
That's such a crucial point. See, our source material, it highlights this key diagnostic factor. To actually be diagnosed with depression, you need to display at least 4 specific symptoms. And it's not just checking boxes, it's about understanding the severity and how much it's impacting your day-to-day life, you know?
And the thing is, it's incredibly common. This paper mentions over 10 million cases in Brazil alone. And globally, depression affects roughly 5% of people. That's huge.
It really is a global health concern. But here's the important takeaway. Depression is both common and treatable. You're not alone, and there is effective help out there.
Okay, so we've laid the groundwork. Depression is complex, it's more than just feeling sad, and it's surprisingly common. Now let's get into how science has tried to tackle this, starting with what our research calls the monoamine hypothesis. Sounds like the title of a mystery novel, right?
It kind of does, doesn't it? And this hypothesis, this was a major breakthrough at the time, really honing in on these 3 key neurotransmitters: dopamine, noradrenaline, and serotonin. Think of them as the brain's internal messengers, constantly sending signals between neurons.
Okay, neurotransmitters. Those always sounded so mysterious back in high school biology class. What are they actually doing in our brains? Break it down for me.
All right, so imagine a relay race, right? Each runner is a neuron, and the baton they're passing is the neurotransmitter.
Okay, I'm visualizing it.
Good. So in this case, those messengers, the dopamine, noradrenaline, serotonin, we're talking about they're regulating crucial functions: mood, motivation, attention, even your sleep cycle gets in on the action.
Wow, so they're busy little guys.
They are. The monoamine hypothesis basically proposes that in a depressed brain, those runners are dropping the baton more often. Those signals aren't getting through quite as smoothly. There's a shortage of these key neurotransmitters in certain parts of the brain.
So if depression is like this messenger shortage, antidepressants swoop in to save the day, right? Delivering those missing messages.
That's the gist of it. And this is where it starts to feel like a real detective's case file, because we have clues. Studies show that if you deliberately deplete those monoamines, people start to experience those classic symptoms of depression. So we're building a case, right?
Okay, so mystery solved. Case closed.
Not so fast. There's a twist. Remember how we talked about episodes having this prolonged impact? Well, antidepressants are quick. They're like sprinters, those antidepressants. They boost those monoamines almost immediately.
Really?
Yeah, really. But here's the catch: the mood improvement. That often takes weeks to really kick in.
Hold on, that doesn't quite add up. It's like giving someone a caffeine boost when they haven't slept in days. But they might feel a jolt, but they're still exhausted.
Exactly. And that's the timing problem that has researchers puzzled, because if it were just about restoring those messenger levels, shouldn't relief be almost instant? It suggests there's a whole other layer going on beneath the surface.
Okay, so we need to, dig deeper. What other clues are out there? What's the next chapter in our mystery?
That leads us to a more intricate layer of this whole investigation, and it's called the neurotrophic hypothesis. If the monoamine hypothesis was all about the messengers, this one zooms in on the health and vitality of the neurons themselves.
So not just whether the messages are delivered, but the actual condition of those brain cells ending and receiving them.
Precisely. And at the heart of this hypothesis is something called BDNF. That's brain-derived neurotrophic factor, for those who like their acronyms.
Okay, hitting us with the jargon. I'm ready.
No worries. I'll break it down. Just think of BDNF like fertilizer for your brain cells.
Okay, I'm intrigued. Fertilizer for the brain. Go
I
on.
know, right? It sounds strange, but it's a good analogy. Just like plants need nutrients to grow and thrive, our brain cells need BDNF. It supports their growth, it helps them make connections with each other, and keeps them functioning optimally.
So you're telling me my brain cells have a stress limit too?
In a way, yes, because here's where stress enters the picture. And I don't just mean the deadline at work kind of stress. This research highlights that chronic stress, whether it's emotional, physical, or even environmental, it can directly impact the levels of BDNF in your brain and lower BDNF. That translates to potentially less brain cell growth, less of those healthy connections forming, and potentially greater vulnerability to experiencing those episodes of depression.
Wow, so it's not just in my head. Stress is literally messing with my brain's ability to grow and adapt.
It's a super complex interplay, but that's definitely a key takeaway from this research. And, there's a specific region of the brain that's particularly vulnerable to this, and that's the hippocampus. That part that plays a crucial role in learning, forming new memories, regulating emotions. All things that often take a hit when someone's experiencing depression.
So let me get this straight. We've got potentially stressed out brain cells, maybe low on that BDNF fertilizer, and a vulnerable hippocampus. Where do antidepressants fit into all of this?
That is the million-dollar question, isn't it? And this is where those two hypotheses we've been discussing, those two chapters of our mystery, they might actually converge.
Ooh, a plot twist.
Right. Because while antidepressants, they act fast, boosting those monoamines, those quick messengers, remember their long-term effects, well, those might be linked to this whole BDNF thing. There's a growing body of research suggesting that antidepressants could, over time, actually support BDNF production, essentially helping those brain cells recover and build up resilience.
Okay, so we've got the messengers, we've got the brain cell health, the stress factor.
Yeah.
This is feeling less like a whodunit and more like a howdunit, you know?
Exactly. And now, with that foundation in place, we can finally open that medicine cabinet we talked about and look at the different types of antidepressants that have been developed over the years. It's like looking at the tools investigators have used to tackle this mystery from different angles.
Right, so we're opening the medicine cabinet, ready to examine the tools of the trade. I'm picturing like that scene in a heist movie where they lay out all the high-tech gadgets.
Okay, I see where you're going with this.
Yeah.
But in this case, forget sleek gadgets. Think more like a historical museum. Our research takes us on this fascinating journey through generations of antidepressants, each with its own mechanism and backstory.
I'm into it. So let's start with the OGs then. The paper mentions something called MAOIs. I feel like I'm about to have to decipher a secret code.
MAOIs, those are monoamine oxidase inhibitors, just to decode that for you. They're like the pioneers, the very first class of antidepressants to really emerge on the scene. And their whole story, it goes back to this enzyme, monoamine oxidase, or MAO. That's the one that breaks down those mood-regulating neurotransmitters we were just talking about.
Right, the cleanup crew, making sure those signals don't stay active forever.
Exactly. So what MAOIs do is essentially they put the brakes on the cleanup crew, they inhibit that MAO enzyme, which leads to this buildup of those feel-good neurotransmitters in the synapses. It's like turning up the volume on those positive signals, And they can be really effective for some people, but, they did come with some downsides, side effects, and some, honestly, pretty intense dietary restrictions you have to be careful about.
Wait, dietary restrictions? Like what? No more cheese plate while I'm contemplating the existential dread?
Not quite that dramatic, but that whole cheese reaction thing you hear about sometimes?
Yeah, vaguely.
Well, that comes from tyramine. It's in certain foods, aged cheeses, cured meats, stuff like that. Normally, MAO breaks down the tyramine, no big deal. But when it's being inhibited by these MAOIs, tyramine can build up and cause a sudden dangerous spike in blood pressure. It can actually be pretty risky. So that's one of the reasons why MAOIs, while they're effective for some, aren't as widely prescribed these days. Just a little too tricky to manage for most folks.
Okay, so MAOIs Effective, but definitely require a strict diet.
Gosh.
What came next in our antidepressant evolution then?
So researchers, they took what they learned from those early MAOIs, kept tinkering, and eventually developed tricyclic antidepressants. TCAs for short.
Catch your name for sure.
Right. And TCAs, they work a little differently. They mainly block the reuptake of both serotonin and noradrenaline. Remember how we were talking about those neurotransmitters being like relay runners?
Yeah, the baton pass.
Exactly. TCAs are like, well, they prevent the runners from being pulled back into the starting line too quickly, so the message keeps going. It has a bit more time to be received.
Oh, I see. So it's less about increasing the production of those messengers and more about making the existing ones work harder, kind of.
Precisely. And, TCAs, they were definitely a step forward in terms of effectiveness, but, and this is a big but, they also came with their own set of potential side effects, often more pronounced than what you typically get with the MAOIs we talked about.
It's like that constant quest for the perfect medication, It always seems to be this balancing act. Effectiveness versus unwanted side effects.
Always. Medicine is rarely simple.
Right. Okay, so let's fast forward to the present day. What about these newer generations of antidepressants? This is where it gets really interesting right now.
Here's where we really get to see how much research has evolved, absolutely. So, enter the SSRIs, selective serotonin reuptake inhibitors. I bet you've heard of these. Prozac, Zoloft, Paxil. They're some of the most commonly prescribed antidepressants out there today.
Yeah, those are definitely household names.
Right. And as their rather long name suggests, they're a lot more targeted in how they work. They focus very specifically on inhibiting the reuptake of serotonin, leaving other neurotransmitters relatively, untouched.
So less collateral impact, fewer side effects, hopefully.
Exactly. And that's a big part of why they've become so widely used. Of course, everyone responds to medication differently. That's just the reality of it. But in general, SSRIs tend to have a milder side effect profile than, say, the MAOIs or TCAs we discussed.
Makes sense. More precise targeting, potentially fewer side effects. Okay, so what other options are there in this newer generation? I feel like the more we talk about this, the more tools we're discovering in this mental health toolkit.
There are. You've also got SNRIs. Those are serotonin noradrenaline reuptake inhibitors. So they're working similarly to SSRIs, but they're targeting both serotonin and noradrenaline reuptake, like a broader spectrum approach, maybe venlafaxine, duloxetine. Those are a couple examples you might recognize.
Okay, so more options, each working on those neurotransmitter pathways in slightly different ways.
Right, because even though these medications, they all fall under that antidepressant umbrella, they're not all doing the exact same thing on this, molecular level, which is why it's so important to work with a healthcare professional to find what works best for you.
Absolutely. Okay, so we've got SSRIs, SNRIs. Anything else in this new generation category? Or are those the main players?
Well, there's one more category to cover, and it's a bit of a catch-all: atypical antidepressants. These are the ones that don't fit neatly into those SSRI or SNRI categories because they have these unique mechanisms of action affecting different neurotransmitter systems and receptors in ways that we're still honestly trying to fully understand. Mirtazapine and agomelatine are a couple of examples if you want to look into those further. But the key takeaway with these is they highlight how complex this all is. There's no one-size-fits-all solution when it comes to something as intricate as depression.
It's pretty incredible when you think about it. We started this whole deep dive with this almost deceptively simple idea, just increase serotonin.
Right.
And here we are realizing it's so much more nuanced than that. We've uncovered this potential link between chronic stress, BDNF, brain health. We've gone from these early MAOIs with their very specific dietary needs to these more targeted approaches like SSRIs. It really has been like piecing together a puzzle, one neurotransmitter at a time.
And like any good puzzle, there are still pieces we're figuring out. That's what makes this field of research so fascinating. There's always more to learn, always more to explore. And the more we learn about these intricate mechanisms, the better equipped we are to develop more effective, more personalized treatments.
It really makes you think, if these medications can potentially influence things like brain cell growth, resilience, that has huge implications for how we view not just mental health treatment, but overall well-being.
Absolutely. This is about so much more than just a pill. It's about understanding the brain, respecting its complexity, and supporting its incredible ability to adapt and heal. And that, I'd say, is a pretty hopeful note to end on.